Okay, so starting in about 5. So we've talked about the first of the 3 greatest unsolved mysteries of the Big Bang, which is where did structure come from, what created the tiny fluctuations about which eventually galaxies formed. We're now gone to the second of these 3 mysteries, which is why the universe is made of matter rather than just antimatter or photons.
So everything in the universe is made up of particles. We have this model that has been phenomenally successful at predicting what we see, and most recently evidenced by the Higgs boson, which was discovered and was predicted by this theory. So the particle world is full of these elementary particles. This shows us all the elementary particles. Well, not all of them, because each of these particles has an antiparticle. That's not actually quite true either, because photons are their own antiparticle. These particles and antiparticles come in pairs, always come in pairs. You can't create one without creating the other. So if you're going to have a photon, you have to produce 2 photons. If you're going to produce an electron, you got to produce an electron and a positron. And so the universe has this beautiful symmetry. Should also just point out, you'll note that there are quarks and there are other things here. There are no protons and neutrons, and that's because protons and neutrons are created out of quarks. But you can have an antiproton. It'll be made up of antiquarks as opposed to normal quarks.
Okay. So in the very early universe, the photons had enormous amounts of energy because, as we've said, as you go further and further back in time, they have more and more energy because their wavelengths are smaller. They have so much energy that they can actually turn into mass. To create a particle with a given mass, you need energy E equals mc squared. So you take the mass multiplied by c squared, that's the speed of light squared, and that tells you how much energy you have. When the universe was very young, the photons had enough energy to, for example, a photon flying along, it could create an electron and a positron. So electron and its antiparticle, the positron. And these 2 particles would go out a bit, and then eventually they'd come back together again, annihilate, producing another photon, which would keep on flying along. So in the very early universe, it didn't really make sense to talk about photons and particles, because photons are always changing into particles, to be precise, a particle-antiparticle pair, and then they'd always change back again. So the universe is a constant seething bubble of photon to particle to photon to particle and back and forth.
And it's not just electrons and positrons, right? You can make just about anything. So, for example, if you want to make a proton-antiproton, you really have some quarks and some antiquarks that are formed. And the same process happens where the photons, if they have enough energy, E equals mc squared, can produce these things, protons, neutrons, or any of the particles in that sea of particles that we showed you earlier.
And you could do the calculation. We showed the equation for the energy of the universe. You set that equal to mc squared, and you can work out how small the universe had to be creating, say, protons and antiprotons or electrons and positrons. But as space expands, the energy gets less and less, and at some point, these are not formed anymore. So whatever particle antiparticles happen to be there at that point, they can get together again and form a photon, but the photon now doesn't have enough energy to create more particles. So what you would think would happen at this point is you had this whole sea of photons and particles and antiparticles, but suddenly you've got a one-way gate. Particle can combine with antiparticle to produce a photon, but it can't go backwards because the energy is too low. And so what would you think is there'd be equal numbers of particles and antiparticles, and they would all meet each other, annihilate, turn into photons, which no longer had enough energy to turn back, and so the entire universe would change to a universe just made of photons.
So that would be problematic because you and I are not made out of photons. We're made out of atoms. So what do you think's the solution to this? It doesn't make sense to me.
And it actually looks like most of the particles did annihilate, because we see there are 10 to the 9, a billion photons for every other particle, and those are the ones left over from the annihilation. It looks like all but 1 part in a billion the particles, antiparticles annihilated and produced photons, but there was a slight imbalance. 1 part in a billion didn't annihilate. So what's going on here?
Well, okay, let's think of it. You must have an idea. What's your best idea?
I don't know, but one idea might be that maybe there was a perfect balance. I mean, the laws of physics seem to suggest that there's a perfect symmetry between particles and antiparticles. Any reaction has the same chance. So maybe the universe today does have an equal balance of matter and antimatter. It's just they're somehow separated, so they didn't annihilate each other. Maybe all the protons are over.
So sort of something like this.
Yes, my simulation, Brian. So we've got all the negatively charged electrons, the normal ones, and the positively charged protons over here. This is the universe that we live in, and this is a universe that everything is reversed. And we couldn't tell the difference between these things. It would be just the same living here, we just define our charges differently. But a universe entirely made of antimatter and matter would be perfectly fine. The trouble would be if they met each other. So it could be that maybe the bits of the universe near us are made of matter, and maybe a distant galaxy cluster is made of antimatter.
Okay, so that would be, quite a lot of fireworks here on the dividing line.
That'd be the problem. I mean, let's say Brian was made of antimatter and I was made of matter, and we came and shook hands. Bang!
We're gone.
You can work out how much. So we weigh about 100 kilograms. E equals mc squared. So multiplied by c squared, that's about 9 by 10 to the 16. So times 100, we're talking about 10 to the 20 joules, which is about 100,000 times bigger than a very large atom bomb.
That would,
So if you meet someone made of antimatter, don't get near them. But if we did have parts of the universe that were made of antimatter and matter, then what is going to happen on the boundary? You're going to get the matter bumping into the antimatter and huge amounts of violence and energy.
And we certainly don't see that in our universe right now. So if it's happening well beyond where light can reach us. I have maybe another idea. It seems maybe a little more strange, but I got to invent something. And what I got to invent is imagine the universe is full at its birth with a sea of normal matter, and then these reactions happen as per normal, and when they end, that stuff it was born with, that extra stuff it was born with, well, that's what's left over. And so you end up with a universe that was born with more matter than antimatter. I don't know why.
It seems pretty arbitrary to me.
Well, okay, but so we need some ideas to figure out why one of our ideas would be right.
And it could be there's just a very slight asymmetry in the laws of physics. As far as we know, the laws of physics of matter and antimatter are exactly the same. But maybe there's some very small difference between them, so in fact these reactions do produce slightly more of one than the other. People have been looking for this experimentally for a long time and haven't found it, but that doesn't mean it doesn't exist. We only need it to be a 1 part in a billion difference, because by and large most matter and antimatter did wipe each other out. So it could be possible there is some very small difference, some asymmetry in the laws of physics that hasn't been spotted yet.
So a big mystery for the future.
Okay, but done.
Yeah,
That's good.
I thought we did a lot better that time than last time.
Yes.